Now I'm going to play a very short video to try and show you how the combination of two plane waves can give rise to standing waves, right? And how these standing waves having to fit within the boundaries of the parallel plate waveguide gives rise to a restriction on the angle between these two plane waves, right. So, let us try to emulate that by a very simple demonstration that I did in my office. I have here a plain white sheet with two parallel red lines to indicate the metallic boundary conditions. I have printed two transparencies with black lines to indicate planes of constant phase. I have overlapped the two films on top of the sheet of white paper, and now if I twist one of the transparencies indicating one plane wave with respect to the other, please note the patterns that we observe. You can see vertical stripes forming, a dark band in the center followed by two white bands and then two dark bands again. The white bands, if we consider that as minimas, and if that happen to line up with the red lines underneath, we can call that as a solution. If I twist this further, I can see that more vertical lines are being able to fit within the same pair of red lines. Okay, so in that video, I hope you saw that the greater was the twist angle, right? That is the angle between the two plane waves, k vectors. The greater the angle was, we noticed that there were more standing waves, right. So, more of the bands were compacted within the two vertical red lines, right. So, what are we essentially doing? Instead of having to solve the Maxwell's equations within the bounded region of two perfect conductors, we are saying that let us consider two plane waves, right, that are in an unbounded medium, and then change the direction of these plane waves slightly from each other, right, and look at the interference pattern that comes from adding these two plane waves. And we are saying that if I were to constrain and look at just the electric and magnetic fields within the two perfect conductors, that when I twist them at a very specific angle, I notice that I am getting a solution of electric and magnetic fields within the conductors that satisfy the Maxwell's conditions, boundary conditions, right, which means that that has to be an allowed solution by the Maxwell's equations, and this is what we are saying is the mode. So, instead of having to solve for the Maxwell's equation, we took a an easy route by just making careful observations, right. So, it is clear that the greater is the twist angle, right. Remember that a greater twist angle between the two waves right. So, if you are calling this as the twist angle, say alpha, alpha is actually the complement of your angle of incidence, right. So, smaller is the alpha, greater is the angle of incidence, theta, right. So, if alpha was very small, that the two plane waves were very close to each other, we will notice that the angle of incidence is very large or close to 90 degrees, right. and we notice that as the twist angle or alpha increases, we are seeing more maximas and minimas being allowed within the waveguide, right. So, this is also very much like the situation that we saw from the equations, right. So, which equation can we take? So, let us say that k1 cos theta I is equal to m pi by d, right. So, remember that the more number of half cycles within the parallel plate waveguide corresponds to higher values of m, right, and higher values of m corresponds to higher values of m correspond to smaller values of theta or the incidence angle, right. Which is what we saw, right. Smaller values of theta or higher values of the twist angle alpha, right. All right. So, let us move to the next topic, right. So, remember that we had a constraint. So, cos theta I was m lambda by 2d, right. So, lambda 1 is 2 pi by k1, okay. This is the wavelength in the dielectric medium that fills the space between the parallel plate capacitor. And we said that cos theta I, the magnitude of it cannot go beyond 1, right. So, we found that there is a constraint on m, okay. So, this implies lambda is less than or equal to 2d by m, okay. So, it means to say that for wavelengths greater than the value 2d by m, we cannot support a propagating mode, right. Why do I say that? So, let us recall the total electric field. It was minus 2j E naught sin kziz e to the minus j kxi x, okay. This is to say that there is a propagation of the wave in the x direction, right. What can we say about kxi and kzi? Since they are just components of the vector k1, right, they certainly obey the Pythagoras relation, right. If cos theta were to exceed 1, remember that kxi would become complex, just like our in total internal reflection case, right. And if kxi were to become purely imaginary, then we would see that the electric field is actually attenuating in the direction of propagation, right. So, this is what we say that the waveguide does not quite allow all wavelengths or all frequencies to go through, right, starting from the parallel plate waveguide itself, okay. And it seems like an upper bound for wavelength, or we can say in terms of frequency mv1 by 2d okay, that the frequency has to be greater than mv1 by 2d, where v1 is simply f lambda 1. Okay, it is the velocity of the electromagnetic field in the dielectric medium, as if it were a non-bounded medium, right. So we can call this, right, so lambda c is equal to 2d by m, and fc is equal to mv1. So if I were to take the equalities, we can call this the cutoff, either wavelength or frequency, right. So remember that frequency and wavelength are inversely related to each other. So it restricts for long wavelengths, right. So extremely long wavelengths are not supported for propagation within the parallel plate waveguide, which in terms of frequency refers to saying that very low frequencies, right, and the delineation between low and high is the cutoff frequency. So in signal processing parlance, we call this a high pass device, right. So this parallel plate waveguide itself, we are noticing that it only allows frequencies higher than a cutoff frequency. Okay. One way to kind of know whether parallel plate waveguides are low pass or high pass in frequency is to just ask yourself the question that if I were to keep two parallel plates in front of me, can I actually see through this structure, right? Because visible light has very high frequency. It is in the order of hundreds of terahertz, right? And of course, the parallel plates are of course at the top and bottom of my vision. I can certainly see through the waveguide, right? Which means optical beams are able to go within the waveguide, right? So optical frequencies are normally very high frequencies, and if they are able to propagate through, it means that the structure allows for high frequencies but not low frequencies, right. Okay, so you can say that it is a high pass device. The parallel plate capacitor is a high pass device.